So hey guys, here in this video we are going to discuss some of the problems which I have chosen, which I felt are at the same level or slightly tougher to the exam which is to happen next month, which is Fizika. And don't worry if you find them very tough, because these are slightly on the medium tougher side, so there will be easier problems too. So no need to worry about that. So in this video we are going to look at 4 problems, and all of them are very similar. So first let's look through the 4 questions. So the first question is from Pathfinder, which is built up your understanding, question number 13 from EMI and AC chapter. So the question is: a thin conducting disk of mass m, thickness d, and radius r, where r is very greater than d, is released in a uniform horizontal magnetic field of induction B. The magnetic induction vector is in the plane of the disk as shown in the figure. Denoting acceleration due to gravity by g, find expression for acceleration of the disk. So this is the first problem. The second problem is again from Pathfinder, from the exercise check your understanding, question number 2 from electromagnetic induction and alternating current from the same chapter. So now let's look at the question. The question is: a conducting disk of mass m and volume v is suspended with the help of a light spring of force constant k from a fixed support. Thickness of the disk is much smaller than its radius. A uniform magnetic field of induction B parallel to the plane of disk is established, and the disk is pulled down slightly and released. Find period of small amplitude of oscillations of the disk. So again, this is a very similar problem. And the third question, let's look at the third question. So this question is from some Allen test series or something, I guess. Someone posted this in my server, and it's a very nice question. So yeah, let's look at it also. Two identical thin circular metal plates are at a small separation d, such that d is very small compared to the dimensions of the plate. They are connected by a thin conducting rod AB of length d. Each plane has an area A. An ideal spring of stiffness K is connected to a rigid support and midpoint of rod AB as shown in the figure. Spring is made of insulating material. The system is on a smooth horizontal surface. Entire region has a uniform vertical upward magnetic field B. The disks are pulled away from the support and released. Mass of the two disks plus the system is m. Neglecting any eddy current, the time period of the oscillation is as given, and we have to find the value of alpha plus beta plus gamma, where alpha, beta, and gamma are integers. So this is also a very similar problem. You should try this. And the fourth question is from some unknown source. I don't know the source for this one. So the question is: consider a rod to be placed on two parallel horizontal conducting rails in a vertical magnetic field B as shown. Now if a capacitor C is connected across the rails and the rod is started to be pulled with a force F as shown, we have to find an expression for its acceleration. So if you want to give this all 4 questions a try, you should do it now. And they are very similar, so if you are able to do one of them, you just try a bit more, and probably you will be able to do all of them. So if you want to try it, you should do it now. So now the hint I want to give to you all for these questions is that both the magnetic and the external forces decides the acceleration. So it's not much of an hint, but yeah, that's all I've got. So if you want to try it again, you should do it now. So yeah, now let's look at the solutions. So let's first look at the first problem. So basically, first let's try to understand what exactly is happening over here. So initially, as there is no velocity, magnetic force is absent and the disk starts accelerating downwards. So basically there's a mg force downwards, and there's no velocity, so there's no magnetic interaction initially, so it will start accelerating downwards with an acceleration of g initially. Now as it starts accelerating downwards, positive and negative charges in the conductor start feeling forces in opposite directions. So basically what I'm saying here is that, let's say a charge positive key is moving downwards, and the magnetic field is as shown, so the force on it will be in this direction, while on a negative charge it will be I have taken the direction to be opposite. If the positive charge is going downwards, so the force on it will be in this direction, while on a negative charge it will be on this direction. So basically, specifically towards the two faces, they will start separating. So basically, they will separate, the charges will separate on the two parallel faces of the disk. Now due to this, some current will be generated, and we can find the force due to this current, and hence the acceleration. So that's the basic idea which is going to be used in all of the 4 problems. So if you understood this, now let's look at how can we apply this. So now let's look at the calculations. So now here is the front view. So let's observe this from this side, so that the magnetic field is coming as if the magnetic field is coming out of the plane. So the magnetic field is coming out of the plane. This is the width of the disk D, and the charges, separation of charges, has been shown along the two faces as shown. Now the radius of the disk is given r, so the diameter will be 2r. Mg force will be acting in the downward direction, and let's observe it at some moment when the its velocity is v. First of all, induced EMF across the faces can be written as v times b times d, where v is the velocity and this capital V is its potential difference. So this will be the EMF generated, or the induced EMF in this disk across the two faces. So due to this EMF, the charges separating at this moment will be Q equals to capacitance times the potential difference, and the capacitance will be just like a parallel plate capacitor having two plates of area pi r square each. So the charge separated on each of the faces at this moment will be capacitance times VBD, which is the potential difference. Hence, the current can be written as the derivative with respect to time of this charge. So the current will be dq by dt, which is CBD times dV by dt. So now, as we got the current, we can write the equation of motion as F effective or F net is equals to mg, which is in downward direction, minus I times L times B. So here we have to observe that as the magnetic field is coming out, so the length perpendicular to the magnetic field is this length, and force will be applied on as if it was a wire of that length moving perpendicular to the field. So the force will be I times D times B. So net force can be written as mdv by dt equals to mg minus d times b times cbd. We have substituted the value of I to be cbd times dv by dt. So on simplifying this, now here we can clearly see that we can get separate dv by dt, which is the acceleration, as dv by dt equals to mg by m plus cb square d squared. So so the final expression for this is this value, and here I have substituted the value of c to be epsilon naught times pi r square by d, which is epsilon naught a by d. So on substituting this, we get this final answer, which is the final answer for the first question. So hope you all got understood this. So if you are understood this, the second problems or all the other problems will be basically the same thing, only slightly in different setups. So now let's look at the second solution. Now the basic idea is the same as in the first problem, and a magnetic force will start to apply when it gains some velocity, which means that as it was initially at rest, there was no force due to magnetic field on it, and charge separation will occur on the two faces as it gains some velocity. So directly jumping into the calculation, assume the position at which the extension in the spring is x and velocity of the disk is v. So here I assume that this x is the distance extension of the spring. So at this moment I have assumed the velocity of v it to be v upwards. So the charge separation will be positive charge on this face and negative charge on the opposite face, as I have shown here. So basically, again the induced EMF will be VB times D, and the charge separation will be same as we did before, which will be capacitance times the voltage, which will be CVBD, and hence the current will be dq by dt equals to CB times D times dV by dt. Similarly, so just as we did in first question, we can write the equation of motion as the kx force, which is acting in the upward direction, mg force, which is acting in the downward direction, ilb force, which is acting again in the downward direction as its velocity is upward. So these three forces should be equals to the net force, and which will be equals to mdv by dt. So and here again we can substitute the value of I from here, and we can separate dv by dt as kx minus mg equals to mdv by dt plus cb square d square times dv by dt. So we got something like this. So what I've done in this step is that I've assumed x to be something like x naught plus x1, where x naught is the kx naught equals to mg, so that I've assumed displacement from the initial equilibrium position with respect to the mg. So and as it's a linear factor, on differentiating it we'll get 0 in this term. So basically we can ignore that, and I just wrote this as kx1 variable, and here dv by dt can be written as d2x by dt square, and here x can be replaced by x1. So basically we got an equation of SHM where d2x by dt square equals to omega square times x. So from here the omega equivalent which we get is k root of k by m plus cb square d squared. So the time period in this will be 2 pi by omega, which will be 2 pi root of m times m plus cb square d squared by k, and the value of c can be written just as we did in first question, epsilon naught a by d, and in the second question we were given the volume instead of the dimensions. That's also not a problem. So here we can see that we were given a volume, and just as we did in first part, we can substitute it and we can get the final answer of time period to be root of 2 pi by omega times 2 pi root of m plus epsilon naught v b square by k. So that's the answer for the second question. So the third question is basically exactly the same thing. The only difference is that the mg force is being like here, though there's no external force. So and we can see from this question that anyways mg was not making a difference because it was a constant force, and on differentiating this twice we just ignored that mg part. So here also it's the same thing. That's what I've written here. Now the question is exactly the same as P2. The only difference is that there is no mg force, but as mg is a constant force, it was only changing the equilibrium position. Hence the time period is exactly same as P2, and AD was written as V in the final answer. Hence the time period is again 2 pi root of m plus epsilon naught v b squared by k, and instead of v we wrote AD, and so we get the constants alpha beta gamma as 1. So alpha plus beta plus gamma will be equals to 3. So that's the required answer for the third problem. So that's the first three problems, and let's look at the last question now. So in this question, this is again a same setup, but it's just a bit hard to observe if not seen carefully. So again here, as it's applied a force in this direction, so it starts accumulating positive charge on this plate and negative charge on the opposite plate, because as due to EMF induced in this rod, the positive charge will start flowing in this direction, so current will flow in this direction at a rate of dq by dt. So again most of the calculations remain same, just as I said. So the induced EMF across the here it's not the faces, here it's across the rod. I had just copy pasted it. So the induced EMF will be V times B times L. So the charge across the capacitor can be given as Q equals to C times V, which will be CVBL. Hence the current is again differentiating this, we get this value. So again writing the motion just as we did, equation of motion just as we did in earlier parts, we get the value that F minus ILV equals to mdv by dt, and again we get the same expression for the acceleration, which is F by m plus cv square L square. So yeah, that's the final answer, and hope you all like the video. Please like, share and subscribe. Thank you.